Hey there, everybody. We're starting up chapter 6. Your tests are almost done graded. I got 9 of the 10 questions graded. I'm either grading the 10th one during lunch today or when I get home from work tonight. But your scores will be up by noon tomorrow, if not tonight. Chapter 6, we already done some stuff with the circle, learning degrees, but now we're going to learn something in chapter 6 called radians, which are much more important in the grand scheme of things. The handout I just gave you, the blank unit circle, is this right here. This is helpful for people that are watching from home. How many people we got? 4. If you go into the modules, click on blank unit circle, you can see what we're working on. And I'll have one up on the screen, but if you want more copies to practice with, you'll have that available. All right, so we got 2 sections today. We're doing 6.1 and 6.2 because they're kind of related, and 6.2 is actually fairly short compared to 6.1. So 6.1 is on the radian measure. And to help motivate this, like why we do this, let me show you where this is going. In calculus, you're going to learn derivatives. And we're going to see if f of x equals sine x. And we're in degrees, then the derivative f prime of x, which I know you don't understand yet, unless you've taken or C calculus before, is pi over 180 cosine x. But in radians, f prime of x, which is listed as ddx of f of x, is just cosine x. One of these is substantially easier to remember than the other. Radians is superior. Or radians are easier to use. Or anything not navigational based. Navigationally based. We've been using degrees for so long in navigation that that's just can't undo history.
Oh, Professor Jones.
Oh, I have not switched over for you. How about them apples?
Not that. I was gonna let everyone know that there's on the Pearson program, if they wanted extra practice, then you can go to, I believe it's study tools, and you can go into the chapters, and you can go to the section. Just in case if someone didn't know.
I'll show them that later. Thank you. That's actually a good tip. You are one of the few that I'm sure do way more than recommended for or asked for homework. These that were in the Mesa Center on Saturdays for 6 hours, pulling up question after question after question after question and just doing them, just grinding them out. All right, so what are these radians? Radian. When the vertex of an angle comes from the center of a circle. Or portion of a circle. a radian is the length when, well, the radian is the angle, there we go, the radian is the angle when the length of the radius equals the length of the arc around the circle. Of the portion of the circle. So if I make go out about that far. And I'm working on a circle going around, kind of like a circle going around. Wow, that is way too far. Is when this length, which would be the radius of our circle, equals this length, which is called the arc length. And it goes by the letter S. And this is the angle theta, and that's in radians. And that is when arc length S equals R. So you can actually find the angle in radians can be found by doing theta equals S over R. So this, what I have listed here, S equals R, theta equals 1 radian. The way I have it listed pictorially. Radians are unitless. There's no degree on them, there's no nothing like that. Sometimes we write rad just to make it extra clear. Sometimes we use rad. But it's not a unit. And you can kind of see that it's unitless. If we look at this equation right here, like if this is, for example, if I had 5 feet over 3 feet, because they're both lengths, the feet cancel out and there's no units left. So you can see that it's just a number. What's the equation for the circumference of the circle?
C equals 2R squared.
Nope. Getting closer, kinda, it's not a square, R squared is in the area.
How many times radius?
Close, it's 2 pi times radius. Circumference of a circle. Is 2 pi times radius.
Which was one that was pi times diameter? Is that the same?
That's actually the same thing.
Same thing, right?
Because 2r equals d,
The one that popped in my head right away, I wasn't sure.
but 2 pi r is the one we're gonna go with. If we look at theta equals s over r. And let's say we do a full circle. A full circle would be 360 degrees. Right? Then I have 360 degrees equals 2 pi r, because we're doing a full circle, so the arc length for a full circle is circumference over r. And we'll see that we get the relationship 360 degrees is equal to 2 pi radians. Which is where that pi over 180 comes from. If I divide both sides by 360. I can see that 2 and 360 reduce. Pi over 180 is a way to converts degrees to radians. If we multiply by it. So if we have theta degrees and we multiply by it, we end up with theta in radians. And if we use that upside down, if theta is in radians, because the pi is like a radian, multiply this by 180 degrees over pi radians. The radians cancel, and this converts radians to degrees. So that pi to 180 ratio is really important. For those of you that walked in late, I did have a unit circle up on the back table. You might want to grab one. We're gonna be using it a little bit. So let's practice doing that, because we've done a lot in degrees. Let's practice converting degrees to radians. If we start off with 108 degrees. We can multiply this by pi radians over 180 degrees. And we get 108 times pi over 180. Now this reduces. Let's see, this is 108 is 9 times 12. And the bottom is 9 times 20. So the 9's cancel out. And I got 12 over 20, these are both factors of 4. And so 108 degrees in radians is 3/5 pi. Give you guys one try. Try negative 135. So what do you guys get?
3 pi over 4.
Did anyone else get 3 pi over 4?
I got negative 3 pi/4.
I'm thinking negative 3 pi/4, but let's take a look at
Negative.
it. I think 135 is 3 times 45. And we got the pi, and then pi 180 is 2 times 90, which is 4 times 45. The 45s will cancel, and I'm looking at negative 3 pi/4. And if you've got it in pi, leave it in pi. Don't get like a radian unit because that's actually less helpful for you. Unless you're needing like the length. You actually need the actual length of something. It's not helpful. As you'll see in a second. If we have something like 325.7 degrees. This doesn't get very clean. You're almost stuck. Leaving it, let's see, if we do 325.7 divided by 180. I could say 1.8094 repeating pi. Or I could probably, let's just multiply by pi here. And say this is approximately 5.68 radians. Because having 325.7 over 180 isn't all that helpful. And let's give you some practice going the other way. So let's try convert these radians to degrees. Eleven pi over 12. I'm gonna put radians for now, but generally we don't use the radians. So we multiply here, we're going the other direction, so we want the pi on bottom. And that means our 180 is on top. And pi's cancel. 180 and 12 are both divisible by 4. I don't know what's gonna end up being. 180 is 4 times 45. And 12 is 4 times 3. $45 is divisible by 3. 45 is 15 times 3. So my 3's will cancel. And I have 11 times 15. Which is how much? 165. Why don't you guys try -7 pi over 6? And maybe -2.92. So we multiply by 180 over pi. What did you guys get? -210. -210. Did anyone else get -210? 180 is, the pi's are gonna cancel. And 180 is 6 times 30. So the 6's cancel, the pi's cancel. We've got -7 times 30 is -210. This one here is just a clusterfuck. It doesn't get a whole lot better. When you do that, you're gonna get approximately, since I got a round here. -167.3 degrees. So before we jump to the next part, let's just take a look at like. Some common denominators and what they, well, like how many degrees it is at a time. So like, let's say we had x over 12 radians. Or x pi 12, x pi over 12 radians. And you multiply by that 180 over pi. We saw up here when we did 180 and the 12, the only thing left was 15. This ends up being x times 15 degrees. So if you've got a denominator of 12, it's a 15-degree increment. Another common one is over 6. $180 over 6 is 30 degrees. So this is x times 30 degrees. Another common one you'll see is over 4. And if you do 180 degrees divided by 4, you get 45. So when you have a denominator of 4, you're looking at increments of 45 degrees. It's going to be really useful in a second when we're filling out our triple. The other common ones you'll see is x pi over 3 and x pi over 2. X is some number. Like 4 or 5 or 7 or 2. In each case, we're multiplying by 180 over pi. 180 divided by 3 is 60, and 180 divided by 2 is 90. So this is going to be x times 60 degrees, and this will be x times 90 degrees. Any questions so far? All right. We're going to use that right now to kind of fill in this part of this sketch. We're going to do the dotted lines. Let's see what it says. It says place the degrees on the dashed and the radians on the solid. So we'll do degrees on these. The dashed lines right there. And we know this is 0 or 360. And the ones we learned already were 30, 45, 60, and 90. These were our special angles. They gave us nice numbers to work with. Nice. Well, as nice as you're gonna get. Square root of 3 is as nice as you're gonna get in some cases. And this was 180 degrees. So if we use the whole reference angle thing, this is 30 degrees right there. I'm going backward. Oop, shit, I wrote it in the wrong spot. That's supposed to be on the dash. If I go back 30 degrees, this is going to put me at 180 minus 30 is 150. This one is 45. So 180 minus 45 is 135. We go back to that one, that's 60 degrees. 180 minus 60 is 120 degrees. I'm gonna do the same thing going the other way. I'm gonna add 30 to get to this one. 180 plus 30 will put 210 there. So that's like plus 30, plus 45, and plus 60 here. 180 plus 45 is 225. And 180 plus 60 is 240. Straight downwards is 270. So to go forward, I added, to go backwards, I subtracted. Here, I'm gonna go do 360 and I'm gonna subtract going backwards here. So that'll be minus 30 there, minus 45 off of 360, and minus 60 there. This is 330 degrees, 315 degrees. Oh, that's where the 360 is supposed to go. That's why they have two lines there. Let's change the way this looks. This is 330, 315, and 300. That's pretty handy. They put one for the full circle and one for just starting. All right, in radians. We know one circle, or not starting out is 0, so that's not changing. 0 times anything is 0, and we already said the full circle was 2 pi. So this is gonna follow a nice little pattern here. This one has a denominator of 6. This one has a denominator of 4. This one has a denominator of 3. And this one has a denominator of 2. And these denominators are gonna mirror across the axes. I will have over 3 right there, I will have over 4 right there. I will have over 6 right there. And it goes the same way down here, over 3 here, over 4 here, over 6 there. Oh wait, I got those backwards, 6 and 3 is down here. Six is always the one closest to the x-axis. And 3 is the one furthest. I'm gonna put the stuff on top because I wanted to just show you that this is doing some symmetry here. If 60 is pi over 3, what should 120 be? 2 pi over 3, right? Because 120 is double 60. That's 2 pi over 3. You're gonna find in this upper left quadrant, quadrant 2. On this circle here, it's always pi times one number lower. So this is 4, I'm gonna multiply it, put the top as 3 pi. This has got a 6 on the denominator, one number lower is 5, I'll put pi there. So up here, top is one number lower. And down here, top is one number higher. What? What, popsicle sticks or something? What the? Oh, maybe pencils, colored pencils?
Yeah, it was just pencils.
So denominator here is 6, the top would be 7 pi. Denominator here is 4, the top would be 5 pi. And this will be 4 pi over 3. Of course, if the full circle is 2 pi, half a circle is just gonna be pi. You need to fill that one in. And every one of these is pi over 2, so pi over 2, 2 pi over 2, this is 3 pi over 2 down here. The way I do this one is double the bottom minus 1. So 3 times 2 minus 1 is 5. This will be 5 pi over 3. Four times 2 minus 1 is 7. This is 7 pi over 4. And finally, 6 times 2 minus 1 is 11. This is 11 pi over 6. Now, this outer stuff is for the XY coordinate, and we're gonna do that part with 6.2 when we're doing the unit circle. So we're gonna come back to that in a second. You will, if you practice this, like if you like try to draw this circle and fill it out. Like 4 or 5 times, you will have these down pretty quickly. You will remember really quickly that the one closest to the axis has a 6 on bottom. The one that's along the diagonals have a 4. And the ones that are furthest are 3 on bottom. The only part where you'll slow down is the numerator. If you're anything like me, the top. And that's where I gotta think what's going on here. But with some practice, you'll remember these without memorizing this as one number lower. It's a handy thing to while you're learning it. I don't think of it when I'm doing it. So, okay, we'll come back to that in a second. So we said theta equaled S over R. And if we clear fractions, we get S equals R theta. This is the arc length formula. And theta has to be in radians. To use this for arc length. So let's say a circle. Has a radius. Of 25.60 centimeters. Question A, what is the length of the arc? Well, both of these are gonna be, what is the length of the arc? What is the length of the arc? When the angle is 7 pi over 8 radians. This one's just fill it in. S equals R was given to us as 25.60 centimeters. Times theta, which was 7 pi over 8. Remember, radians are unitless. So the only units we actually have here are centimeters. And if you leave the pi in, you've got like 22.4 pi centimeters, which should be pretty much meaningless to most people on the planet. So if you multiply that out, this is approximately 70.37 centimeters. I have that written down in my notes. Let me just make sure that 25.6. What I'm doing is 25.6 times 7 divided by 8 gives me the 22.4. And now I'm going to multiply that by pi. And I get 70.37. I get a whole bunch of numbers. So what my calculator actually says, the calculator shows 70.37167544. This is not exact. I saw this on the test. People doing the calculator when asked for an exact and an approximate. That is not the exact answer. That is exact.
All of trigonometry is not supposed to be exact. Is that right?
Yeah, well, pi is an unending number. Notice, like, I'm gonna show you that there are more decimals than my calculator shows. I'm gonna take that number and I'm gonna subtract. I'm gonna do minus 70.37167544. And if that was an exact number, subtracting this should give me 0, right? But it doesn't. So this is showing me there is more decimal places after that. The calculator only shows so many. Even computers will only show so many. Some programs will show you, some apps will show you 20, 30 fucking decimal places, but it's still, they're rounding when it runs out of room to show you what it is. So the exact one has something like a pi in it, or when it was in terms of like the test, leaving it at like one of the ones was 100 times tangent of the angle. Leaving it in terms of the trig function would be exact. All right, so what would I do if the angle is 54 degrees? So if I go down the same path, R is 25.60 centimeters. And theta is 54 degrees. Now I have two forms of units. I have centimeters and I have degrees. I don't want degrees. That means we need to turn it into radians. So we can turn that into radians right now. We'll multiply this by pi over 180 degrees. That will clear the radians or degrees. And give us a value we can use. This ends up being 7.68 pi centimeters. Or to be useful, approximately 24.13 centimeters. And let's take like a 10-minute break. It's been almost an hour. One of the classes. Alright, let's do another example. We got a couple more examples, then we're gonna do another thing in this section. We're almost done with 6.1. Let's say we have like a winch. We have a winch or which is like a wire on a drum. We have some spool of wire. Like you have it hooked up to a Jeep and your fucking winch is going and you're pulling some shit. Let's say the radius of this thing, the radius of the winch is 0.327 meters. Around a foot. And the rope just, or the wire, like your cable, just keeps getting wrapped around it. It keeps getting wrapped around it, builds up on it, or you let it out kind of thing. How much rope is being, or how much cable is wound up? When the drum or winch rotates. Through an angle of 132.6 degrees. Where are you gonna really use this in real life? I don't know, but if you like needed a certain length of rope or cable. And you can like, and you could know how big the drum is, you can figure out how much you need to unravel it. How many rotations you need to, crank it out to get fairly close. Same thing going the other direction. If you're in engineering, this is a pulley system. There's a lots of applications of this. We're still doing S equals R theta here. R is 0.327 meters. Theta is in degrees. And we don't like meters and degrees, we just want meters, so we need to clear degrees. So this is our theta, that's our R. You multiply that out, you're gonna get approximately 0.757 meters. You should do that on your calculator, see what you get, make sure you get that. And why did I decide to go to 0.757?
The meters were 3 spaces out.
The meters was the smallest number of significant digits, so we had 3 significant digits here. 4 digits here, we use the smaller one. What?
Since we have one number that is 3 digits, that's 180.
Well, the 180 is part of what we did as the conversion,
So it's
that's not part of what the given data. Yeah. You wanna go off things that have been measured. Those are the ones you wanna do, and we measured this. There's no way they had 0.327 without some form of measurement. Same thing with that. There's no way you would estimate 132.6 degrees ever. I don't even know that I could do very well at 130. You know, I can do this, the 60 to 45 and 30 kind of thing. Alright, next one here. In fact, my friend was working on something and he asked me to do something very much related to this. This is the double gears one. That we're gonna do. Does anyone need a longer? Alright. So we've got 2 gears that are connected or. By their teeth. So we got a little gear and we got a big gear. And when I say teeth, they have little ridges on them. These are the teeth. And let's call that R1 and let's call this R2. Big gear and little gear. There's a motor on the smaller gear. A motor on the smaller gear rotates it. To make the bigger one rotate. Let's say R1 is. Let's go give the problem real quick. If the smaller the gear rotates 150 degrees. How much does the bigger one rotate? If R1 is 3.6 inches. And R2 is 5.4 inches. So pictorially, what's going on is this bad boy is rotating 150 degrees. And that causes this one to rotate as well. But how much? The idea is since they're touching together. The arc length moved by 1. By the little gear. Forces the same movement in the big gear. Length of movement in the big gear. They're kind of like R1 theta 1 has to equal S. But that should equal R2 theta 2.
Do we have to turn degrees into radians first?
We will, yes, we'll definitely need in radians. Cause this is using, since we're using arc length to do it. We're gonna need it in radians. Now, what are we looking for here? We're looking for how much the bigger one rotates. This is what we want. So you have two ways of doing this. You can. Option 1. Calculate S. Then use it in. Then use it with R2. Option 2. Make it one equation by eliminating S. That's by going R1 theta 1 equals R2 theta 2. So theta 2 is gonna equal R1 theta 1 over R2. I'm gonna do the longer one, option 1, just because that's probably what most people will do. But it will work on both. So S is gonna equal. The little one. We're doing R1 theta 1, that's the one we have information on. 3.6 inches. Times 150 degrees. And we don't like 150 degrees, so we're gonna do pi over 180. Or if you memorized it from the last section. 5 pi over 6. Six, not 16. .6 times 5 divided by 6 equals 3. This is 3 pi. That's convenient. That's too convenient. Wow, perfect number. So this is 3 pi inches, and then we'll do that with. S has to equal R2 theta 2. So 3 pi inches. Equals 5.4 inches. Times theta 2. So theta 2 is. We divide both sides by 5.4 inches. Theta 2 is 3 pi over 5.4. And I'm gonna multiply this by 180 over pi to get back to degrees. We started in degrees, we want to end in degrees. So pi's cancel out. 3 times 180 divided by 5.4 is 100 degrees. So I had to rotate less. But he wants to use this, he lives in Colombia. He's gonna have a stream flowing. With a water wheel on it, one. Presumably the bigger wheel is on in the water. And it's gonna be linked. Actually, with like a pulley thing, like a 10-speed bike, rather than interlock, 10 speeds work like this as well. Cause it's still, the teeth are connected by a chain, and so one turn. And that makes the little one spin faster, and that one's gonna generate electricity, so he's making his own. Hydroelectricity. And he's like, how can I maximize? Cause the electrical system down in Colombia apparently just fucking shuts down randomly. Mail system, so he does a lot of shit with it, I don't know why he was down, I know why he was down there. He met a woman that lived down there and he loved her and he married her, so he was there. Rather than her coming to America, I don't know. But we were working on this just a couple weeks ago. Alright, last thing in this 6.1 section is area. Area of a sector. Area of a sector, well, let's do the area of a full circle. Is pi r squared. The area of a sector. Is 1/2 r squared theta. Okay, and again, theta is in radians. So let's just do an example here, find the area of a sector. On a circle. Radius 5 miles. Say 5.0 miles. And a central angle of 6 degrees.
What if you don't have a set line? Set two angles.
What do you mean?
What if we
Like pictorially what we're doing here. In fact, maybe I should have done this up here. We sweep out an angle theta. And we're looking for this region in here. So that's an angle theta. So we're looking for the area of that portion. So we're gonna go through and do it. Area of the sector is 1/2 5.0 miles squared. We have 6 degrees times, we need that in radians, 180 over pi degree. Nope, other way around. I need the degrees on bottom. And I fucking did it again. Pi over 180 degrees. And let's see. 5 squared. Times 1/2. Times 6. Divided by 180. This is 0.416 pi. Miles squared. And I'm getting 1.3089969939 is what my calculator shows. And we only had. Let's say that was 6.0 degrees, just to make this a little easier. So we should only have it to 2 decimal places, 1.3 square miles. Now, if you have problems remembering area of a sector is 1/2 r squared theta, and you likely will, because I do. A way to remember it is, do a relationship. Area of sector over area of circle. We're gonna compare that to S over circumference. These are both mid lengths on the outside, these are both areas. You have area of S over pi r squared equals r theta over 2 pi r. So if you multiply both sides by pi r squared. You really got pi r cubed theta over 2 pi r. And one of the pi's cancel, or the pi's cancel. One of the radiuses on top cancel with the radius on bottom. And you're left with pi r squared theta over 2. I literally do this when I need like the area of a sector, because I do not remember the formula. Not confidently enough that I go with it, so I just like, I memorize the circle and I know this, and I know this. Those are 3 easy equations, 2 of them hopefully you've known for a while. S equals r theta may be new. I don't know if that helps you or not. Stop this video so we can start a new one for 6.2.